Hello, once again. So now I was presented with one of the problems that is fairly common in the theory of graphs, that of finding equivalent conditions to describe a tree. So I'll start with this, right? So let T be a graph that is connected. We're going to show that the following two are equivalent. T is a cyclic, and for vertices U and V in the collection of vertices of T, there is a unique simple path from U to V. What is a simple path? A simple path is a path with no repeated vertices, right? In other words, it's just essentially a string of symbols starting at U and ending at V, where we show contiguous symbols indicating an edge between any two vertices. So to this end, what we're going to do is we're going to proceed by contradiction and obtain the desired results. So let's start with this. So we're going to suppose that T is a cyclic, meaning it has no cycles, while there are two vertices, U and V, with different simple paths, with two different simple paths from U to V. So we're going to describe them just like this. The first path starts at U and then proceeds with an edge, and then it lands at another vertex, and then it proceeds with another edge, and then it lands at another vertex, and we'll continue in this fashion until we get to this point, something along these lines. En, Vn, which would be just the last one, right, that we introduced. And well, here's another path, P2, different from this one, possibly of different length as well. So U, E1 prime, V1 prime, E2 prime, V2 prime, continuing this function, EM prime, V. All that we know is that they are simple, there are no repeated vertices here, there are no repeated vertices here, but they start and end at the same point, right, at the same vertices. So pictographically, it kind of looks like this, right? You have U here, and you have V here. What we're indicating is that we can move following a path along these lines, and then we can move in a path along these lines. But then immediately, look, this is what we obtain. From this picture, what we can obtain is by concatenating these two paths, we can obtain a circuit. A circuit from where to where? Well, a circuit that starts at U and ends at U. But then look, what is the complication here? Well, even though this might be a circuit, there might be some repeated vertices. Every circuit may be reduced to a cycle. as there's a very similar result that indicates that every path might be reduced to a simple path by properly deleting the repetitions. So if we proceed in that fashion, what we have is a circle that might be reduced to a cycle, but then there is a problem because this says that T has no cycles. So a contradiction. And well, we backtrack and we see that the only assumption that we made is that T is acyclic while there are two different simple paths joining U and T. Well, now let's go for the second portion. Right? This second statement implying the first. And well, once again, we'll proceed by contradiction. Let's suppose that for every two vertices, there is a unique simple path from U to V in T, while T has a cycle. Well, and T has a cycle. In other words, it's not acyclic. Oh, imagine the picture. No? If T is somewhere here encoded somehow, right? See that T is here. And what we observe is that, well, we have a few vertices here in T that form a cycle of some length. The length of the cycle should be at least 3. So, of course, there are no cycles of order less than 3. So, well, let's give it a name, right? So, let's call this cycle C. But now you can imagine, right? It contains at least 3 vertices, right? Okay, kind of like this. This is my U, this is my V, and there might be some W floating there, right? Who knows, right? But then look, once that is possible, we will be able to construct 2 paths different. One joining U with B, avoiding W, and another one from U to V, including W. Then we can construct 2 different simple paths from U to V. One including W, the other one excluding W. A contradiction. Well, with this we finish, because now we have demonstrated that T being acyclic implies that for every two vertices in B, there is a unique simple path joining them. And, well, whenever we assume that for every two vertices, there is a unique simple path in T joining them, well, then the graph itself is acyclic. So that says that these two are really equivalent conditions. So we may use whichever one we like to define trees. Okay. So with this, we finish, and I hope that you enjoy it. Thank you. And if you like more videos like this one, please subscribe. See you around.